Alright, question 7. Hex 3-ene, we actually talk about 6 carbon. So 1, 2, 3, 4, 5, 6. And hex 3-ene. So that means on the third carbon, I will have a double bond. And over here, check that each carbon has 4 bonds. So that means this carbon 3 have 1 more bond to H. Similarly for over here. Okay? But they say occurs in 2 isomeric forms. But cyclohexene occurs only in 1 form. So based on this, right, the isomers, what type of isomers do you think they are referring to? Very good. Must be cis trans, right? So over here they say draw the displayed formula of the 2 isomers and explain why such isomerism is not possible with cyclohexene. That means if it is a ring and double bond, can it exhibit cis trans? No, right? Okay, so based on this, can you check your work? Hex 3-ene can exhibit cis trans. How do we see cis and trans? Okay, you can check that there's a H and H on both sides of the double bond, so it must be trans. Okay, alternatively, you can also look at the bigger groups, right? These 2 big groups are opposite, so you can also say that it is trans. Is it okay? And make sure that you show it is displayed. Okay, question 1 is displayed. And the other side, for cis, right, you have a H on the same side, so it's cis. Is it okay? This part, everybody clear, right? Yes? Okay. So I can move on? This part, yes or no? Yes, this part is easy, right? Yeah. But of course, there's still another part to the answer. Is the other part is talking about the cis trans. It cannot exhibit cis trans because of ring strain.
What strain?
Ring strain. Okay, so take note of the next part. It cannot exist in stable trans configuration due to ring strain. It can only exist in cis, okay? Because if you draw out cyclohexene, right? Cyclohexene looks like this. Okay, and you have 1 H and 1 H over here. So obviously it is on the same side, so it must be cis. Correct? It must be cis because it's on the same side. Okay. Is it okay? Can Can. Can. Okay. Can, we are at 7B. So for 7B, right, they say describe the mechanism. Describe the mechanism of the reaction between hex 3-ene and liquid bromine. So over here, hex 3-ene again, 1, 2, 3, 4, 5, 6. And on the third carbon, there's a double bond. So over here is H and H. And you have liquid bromine, so it's Br, Br. Agree? Br, Br. So over here, double bond undergo what type of reaction? Still recall? Electrophilic addition, correct. So electrophilic addition, then they want the condition. Room temperature. In the dark, correct. In the dark is to prevent what? Correct. Prevent free radical substitution. And let's take a look at the actual mechanism. Okay? Actual mechanism, right? Wait, erase all this first. Actual mechanism, take note of a few key things. Again, we always go from double bond because double bond is electron rich. And the Br always label delta plus and delta minus. Correct? Then goes from electron rich to electron poor. And after that, your single bond must break. So the 2 electrons will go to the Br. That's why at your Br you see the 2 electrons here. Is it okay? And with a minus sign. Then after that, take note. If your Br gets attached to the first carbon, the other carbon will have the positive charge. Everybody follow? Yeah. And then over here, right, does it matter which carbon you add the Br to? Does it matter? No, because the alkene is correct, symmetrical. So in this case, symmetrical, right, it doesn't matter whether you add the Br to this carbon or this carbon. Okay, so this part is called a carbocation. Okay, you also need to label carbocation. And at the same time, we call this an alternative name is what? Another alternative name for this carbocation start with I, N, T, E. Correct. Intermediate. So for intermediate, right, we always form it in the slow step. Why is it slow? Very good, because you break covalent bond. Okay, you break covalent bond is slow. So take note, your intermediate always must be used up. And you notice this part, the Br is this Br. Then the intermediate is the same. So your lone pair, electron rich to this one, electron poor. So the arrow goes in this direction to the electron poor. Okay? So plus and minus attract. That's why the reaction is fast. Correct? And you should get the Br joined to this carbon. Is it okay? So this is the mechanism. For Jade, right, she asked that the CH2, CH3, can we draw displayed? That means you show all the bonds. Can. It doesn't matter. As long as you show all these delta plus, delta minus, lone pair, arrow, all these are the key points, plus the slow and fast. Okay? Okay. Then ask, right, because this part is a H, right? Then by right you add the Br should put on top, right? But now I actually switch, I put H on top, put Br below. Is there any difference? No, it's actually the same. Okay, Ken, it's the same. Oh, you must put the carbocation. It means you label carbocation. But the step, like for example, step 1, step 2. Step 1 is the formation of carbocation. You know that step name, don't need to write. But for free radical substitution, all the steps you have to indicate. Okay? So I can move on from here? Yes. Can I? Okay. Okay, the next part. The next part, right, they say draw the structures of all possible products formed when a small amount of aqueous NaCl is added to the reaction in B. So you have aqueous NaCl. Aqueous means what do you have? OH. Okay, if you are saying OH minus, right, it only comes from alkaline solution. So water, just you have H2O only. Okay, so you cannot use OH minus here because OH minus is for alkaline solution. Is it okay? Then for NaCl, of course you have Na plus and Cl minus. So based on these three, right, you go up to the mechanism again. You notice the only place whereby the nucleophiles, do you still recall what is nucleophile? Nucleus loving. That means you yourself have what? No. You have a negative charge and lone pair. Okay? Negative charge and lone pair. So, yeah. So, based on this, you notice that the nucleophile come into play here. So that means your nucleophile is only relevant in the second step. The first step already occurred. Everybody okay? Whatever other things you added in, right, this first step will always occur first, no matter what. So no matter what, you will get this carbocation first. Then after that, your Br minus will come and attack to get the Br here. Agree? If you have your Cl minus, again it will also attack. Then you get a Cl here. If your water H2O with a lone pair, it will also attack and you get OH. Everybody okay? What is the similarity between all these three products? What's the similarity? Over here, this Br atom, does it change? No, right? Because all these products come from the same intermediate. There's only one intermediate because it came from the first step. This first step will always happen no matter what. It will happen first, it will produce this, then all the nucleophile come in and attack it. So all the products will have this Br. Is it okay? Can? So that means your product, you will actually have exactly the same Br, only this part will change. Can? Out of these three, right, which one is the most major? Yes, correct, this one? Major. And take note, all these products come from the same intermediate carbocation. Okay? And then the rest with the Br and the Cl, they will be minor products. Okay, they will be minor products. They come from the same intermediate because the first step will always happen first no matter what. Okay, let's see. Okay, class, can I move on to part D already? Yes, can? Okay, for part D, right? Okay, they say explain why the reaction of either isomer of hextriene, it reacts with hydrogen bromide, gives the same equimolar mixture of two isomers. Okay, firstly, this either isomer of hextriene, right, refers to what type of isomer? Sorry? Hextriene must be cis trans, correct. Okay, this isomer must be referring to cis trans isomer. So over here, it doesn't matter. So let's see, cis 1, 2, 3, 4, 5, 6 hextriene. So it looks like this. When I add HBr, right, what is the rule that we talk about again? Correct, Markovnikov. So over here, I actually have one hydrogen attached to this carbon and one hydrogen attached to this carbon. Both have the same number. Doesn't matter, right? Doesn't matter. So it doesn't matter where I add the H2. So I will just add the H to this carbon. Of course, remember to take away one bond because I break. And then, is it okay? So based on this, right, which carbon is chiral? Which carbon is chiral? On the right. Correct. The one with the Br. So based on this, let's do a quick check. This one is chiral, so I have one different group, two different group, three different group, four different group. Is it okay? This is a four different group. So take note, over here, C, this part actually just means a CH2, CH3, right? Then this part is actually CH2, CH2, CH3. Can you see? So that means, can you look at your question? The question says produce 1:1 ratio of each isomer. So now this isomer refers to what type of isomer? Say again? Optical, correct. So this one will give you the optical isomer. And why is there 1:1? Because you have what? Correct, you have mirror image. So you have to draw the mirror image and then again come up with the template, right? This one. And then again. Okay, so you notice we have two big groups. CH2, CH3. So I prefer to put it on top, right? So I have CH2, CH3, again, CH2, CH3. Then I check again, I have another big group, so I will place it at the bottom. CH2, CH2, CH3. So over the other side is the same, CH2, CH2, CH3. Is it okay? Then after that, I have left with H and Br. I can place it anywhere. I can place H here, Br. So reflect, so Br and H. Is it okay? Yeah, and one last part, the non-superimposable mirror images, okay? Can everybody? And take note of how you draw the carbon. The carbon here must be linked directly to this carbon because, and then can you put C3H7? No? No, Anybody put C3H7? Not correct. C2H5 similarly cannot. And if anybody do this, like for example a wedge bond, and you put something like this, CH2, CH2, CH3, this one also cannot. Okay, take note of the details in drawing. And the bond must be bonded to a carbon. Similarly, this to a carbon. Can? Okay, right. This part. Can. There's still an explanation to this. Can I move on to the explanation? The written part. Okay. So this part here simply just it reacts via electrophilic addition. Okay, state the reaction to form a product which is 3-bromohexane, chiral center, because connected to 4 different groups. So there are equal proportions of the optical isomer product which exists as a racemic mixture. This part. Is it okay, everybody? Can I move on to question 9? Oh no. Okay, question 9, right? What I will do is I will upload to LMS. Is it okay? Can you go ahead and check on your own question 9? Because now I want to focus on planning already. Is it okay? So for alkene, right? Recap again. For alkene topic, during our tips lecture, we went through the most important things about alkene is you need to know Markovnikov rule, where you add HBr. After that, another reaction is when you do electrophilic addition, the mechanism. And For electrophilic addition mechanism, the intermediate is always what? Always a carbocation. Correct? Remember, radical as an intermediate is only in where? Free radical substitution. So, recap again. For your electrophilic addition, your intermediate must be a carbocation. This one is the main thing you need to take note of. Is it okay? And then what is another thing? For oxidation, remember we went through oxidation. When you cut the double bond, you need to put the O and the O. And then all the H at the carbon bond become OH. Okay, so need to think of these few things. So for question 9 of alkenes, everybody, I will upload to IMS. Is it okay? Then I would like to move on to planning now. That intermediate is actually not referring to the usual intermediate, because question, the last question, right, is actually you have to synthesize. It's different steps. It involves quite a lot of yeah, I think at least 2 steps, maybe 2 or 3 steps. Yeah, recording just in case you miss out anything, but of course for best purpose sake is whatever we do it here, just do it now, then go home, don't need to.
Hi, I'm on camera. Oh,
okay.
Recording.
Your voice is on camera?
Yeah.
Okay. Okay, next this part, let's take a note. This question is actually, are you ready? Yes. This question is actually 2010 A-level question. Yeah, so let's take a look. It's quite interesting. So we say for iron, right, usually it is Fe2 plus or Fe3 plus, right? But it's possible for iron to have Fe plus 6, okay, plus 6 oxidation state. And when it is plus 6, right, it is in this formula, FeO4 2 minus. And can you please highlight this part? For titration, right, we are always concerned about color change at endpoint. So this part, they tell you that it is dark red. Okay? And over here, they say that it is a stronger oxidizing agent than KMnO4. If it is a stronger oxidizing agent than KMnO4, of course, it just means that it is also an oxidizing agent. Agree? And, okay? And over here, they say acidic conditions, FeO4 2 minus is reduced to Fe3 plus. So that means we can actually write a reduction half equation, FeO4 2 minus to become Fe3 plus. Agree, everybody? Yeah. Right. Then for acidic conditions, right? What type of acid can we use? What type of acid can we use? We can use dilute H2SO4. Yeah. I think at this point in time, can you all add in this part? For redox titration, require acidic medium. Redox titration needs acidic medium, right? The only acid that's possible is dilute H2SO4. Okay, this one is only dilute H2SO4. Okay, only dilute H2SO4 is possible because for HCl, it will be oxidized. Yes? For HCl, take note. HCl, if you use it, the KMnO4 will oxidize it to Cl2 gas. Yes. Yeah, you need to know how to explain if need be, okay? Yeah. So that means HCl cannot be used. Of course, if you use it, you will see Cl2 gas coming out. HNO3 itself is an oxidizing agent. Okay, HNO3 is an oxidizing agent. So if you already have KMnO4, then why do you need another oxidizing agent? So don't need. So just use H2SO4. Cannot any other acid, just H2SO4. Correct. Any other acidic condition, you can just use H2SO4. So based on this, right?
Will there be any time when you apply here?
Alkaline medium, huh? If it is alkaline medium, right, you just add NaOH, all this.
But they'll say that in the preamble.
Yes, in the preamble, they will just say acidic condition or alkaline condition. Can? Okay. So this part, right, let's see. A student was given a solution Fa1. Okay, this Fa1 contains potassium ferrate, and she was asked to find concentration of FeO4 by titrating against standard solution of C2O4. Okay, and they tell you that this C2O4 is oxidized. So over here, this must be an oxidation half equation. Anyway, how do you see? Oil rig, right? So oxidation is lost electron. So lost 2 electron. And she actually tested the 0.1 mole per dm cube solution. She found that 10 drops of Fa1 is our FeO4 2 minus. When suitably acidified, that means using H2SO4. Okay, it requires 32 drops for complete reaction. That means over here she find that 32 drops is too much already. Because imagine this is 1:3.2. So 25 cm cube, you will need 80 cm cube, right? 80 cm cube already exceed the burette, but we say cannot exceed the burette. That means the concentration is too low. You need to prepare a more concentrated one. Is it okay? So Syed, right? Based on part A, they say construct a balance equation. Do you all need me to go through with you this question? No. So
I just read down.
Huh?
I lost my one I did.
Okay? Pao Echo, you all go and recap again on your own. Is that okay? Over here should be 3 electrons. Everybody okay? The second equation over here is taken from the question. You try balancing it again. If you cannot get it, then you can ask your friends or ask me.
Will you come a question like that?
Yes. Mole concept is everywhere.
No. As in like when they ask me the planning question, will they ask that?
Yes, the planning question that you will see, right, is very similar to the format of the questions that we're going to go through. Okay, Syed? Can? Okay, so I move on now, this part. Is it recording? Yes, it's recording. So, okay, next, so this part, take note, she say explain why. This part, she say explain why the solution is unsuitable. This part, can you all just quickly take down, very quickly. 10 drops require 32 drops. So the titrant will be 3.2 times more than the analate, okay? Titrant and analate is just a term. Titrant just means in the burette. Analate just means in the conical flask.
Can be anyone.
Huh?
Or was it all 4 points?
Yeah, all 4 points. So typically, right, we know that the volume is 25. But now the volume of the titrant will be 80. 80 because 25 times 3.2 times. It will exceed the volume of a typical burette, which is 50. Hence, it is too diluted and hence not suitable. Okay, y'all try and see who can copy fastest, Huh? Yes. I think you all jot down the key points. You all just jot down the key points because it is still important. Otherwise, when you go home, right, you have so many things to do. Then maybe you don't want to go on LMS already. Just take down whatever you can. Be time efficient. Whatever time you are here, just take down as many things. The main idea here is point number 3. That's the main idea. Okay. I'll move on in 1 minute. Is that okay? Yes, okay, great. Okay, next one. Calculate the mass of solid anhydrous Na2C2O4 required to prepare this Fa2 solution. No, nothing. Thinking process, take note. Okay, you need to find the new concentration of the C2O4 first. Cause the 0.1 mole per dm cube is too low. Okay, which will result in 80 cm cube. But so in this case, some of the principles we need to assume that the volume used is 25 cm cube. Okay? So based on this, right, everybody take note. Assume that it's 25. Listen first, you can use C1V1 equals to C2V2. If you use 0.1 mole per dm cube, your volume will be 80. Do you agree? But now you don't want 80, you only want 25, right? So I must fix the 25. Then from there, I can find the new concentration, which is 0.32. Everybody okay? Can. And then in this case, you know that you need to prepare a standard solution. Whatever solid that you have, right, we always prepare standard solution before titration. Okay, Said? So based on this, you have to calculate 250 cm cube standard solution. Hence, the amount needed is just concentration times volume. That means you will get 0.32 times 250 over 1000. This will give you 0.08 moles. Is that okay? Can? So based on this, right, you have the number of moles, you can find the mass. Okay, just multiply by the MR. You should get 10.7. Everybody okay? So for this question, the two main things that you need to assume, right, in order to do is this. You need to assume that the volume is 25. Then you can use C1V1 equals to C2V2. Then after that, you need to know that 250 cm cube of standard solution must be prepared. Is it okay? So now if you will ask a question, what if I don't know about the 25 cm cube and the 80 cm cube? Then how do I do, right? It is still possible. Very easy. You know about the 10 and 32 drops, right? Same thing. C1 V1 is equals to C2 V2. If I use 0.100 concentration, the number of drops that I use is 32 drops, correct? 32 drops. 32 drops. I just take 32 at 32 cm cube lah, okay? Concentration I don't know. Volume I assume it to be the same as the 10 drops. I want 10 is to 10, 1 is to 1. So that means 10 over 1000. Based on this, I can also get C2 is equal to 0.320 mole per dm cube. Is everybody okay? Can I move on? Okay, last step already. Okay, the next part D, part E, is important because it talks about the procedure. So for these two procedures will be the one that you need to know for mid-course. Okay. Okay, can? So I move on. Okay, write a plan for volumetric analysis. Okay, over here take note, when you want to write a plan for volumetric analysis, right, you need two things. Prepare standard solution. That's the first one. You need to know for mid-course. Number two, actual titration procedure, which we also mentioned to you in the lecture. So for essential details, take note. It just means that you need apparatus and their capacity. Okay, apparatus and their capacity. And you need the volume and concentration of reagents. Mass of the solid also need to specify, and then finally detailed procedure. Think of it as cooking. For cooking, you give the recipe book, right? You need to tell the person after 10 minutes stop the fire, put in some salt. When you see that the fish is brown, overturn. You know these things? Same thing for the planning.
Don't worry, Jay, you're not inside, you already know.
Yeah, good. Can everybody? So I move on. Okay,
Jay, you ready to go out?
that one is different. Okay, this one, prepare standard solution. Everybody please take this down. Plus, for your own paper, right, your procedure is actually given to you as one full 10 steps. Can you break it down into, firstly, prepare standard solution? Can I continue? Can. So firstly, break it down into prepare standard solution. Let's take a look at the diagram. Class, for prepare standard solution, right, I would just want you to take note. There are two different types of preparing standard solution. Number one, you have a solid dissolve, then you get a standard solution. Number two, you need to prepare a standard solution when you have a very, very concentrated solution. You want to dilute it. Is that okay, everybody? So for this planning, right, we have solid. So we are talking about the first part where we are meaning solid dissolve. Everybody okay? Can? So based on this, right, check. Your previous part you actually calculated. You need 10.7 gram. So next part you also need to use 10.7 gram. Okay, so weighing balance, you weigh 10.7. Okay, use a mass balance. Take note, you need to have a very detailed procedure. You assume that the person carrying out the experiment don't know what to use, so you must tell them what to use using mass balance. Weigh 10.7 into beaker. Okay. Then after that, after you have the solid inside the beaker, what do? Dissolve in what? Dissolve in dilute sulfuric acid. Correct. Okay, take note over here. What is the purpose of dissolving in sulfuric acid?
Acidic medium.
Correct. Acidic medium. Okay, class. There's one thing I want all of you to take note. If you are using KMnO4, but you don't have acidic medium, what will happen? What will you form? Add on to this part.
CO3 minus.
Not CO3 minus. If medium is not acidic enough, what will be formed? Remember the solid? You will have brown MnO2 PPT form. You all still recall this from someone? This part, everybody please take down. Remember this part important. Brown MnO2 PPT. Pay attention. Okay, you dissolve it in dilute sulfuric acid. And take note, this part over here, right, the 1 mole per dm cube is actually not given to you. Okay, you have to suggest this on your own. And usually it's 1 mole per dm cube. You know, it's quite concentrated. It's to ensure that it is acidic enough. Okay, and use 50 cm cube. Okay, use 50 cm cube so that it will be in excess. Use 50 cm cube so that it will be in excess. Can. After you dissolve it already, Jade. Okay, after you dissolve it already, what do? You transfer to the volumetric flask, not titration flask, huh? Okay. Yes. Can. Okay, for planning question, right, if they never give you 50 cm cube and 1 mole per dm, you have to give it on your own. But if they already state it in the question, you can just use the question. Is it okay? Okay, over here you must definitely use 10.7. You cannot say use 5 gram. Okay, shh. This part is important because the question says use 10.7 gram so that when you prepare the solution, the concentration will be just right to give 25 cm cube of titrant. Do you agree? So if you use less than 10.7, later after you prepare, your concentration is still too low. You know what I mean? So you need to use 10.7, cannot use 5. Okay? I need you to change your paper, change the solution to dissolved solid and it's washing. Because remember, every time you do titration, you remember this diagram, you use the distilled water, wash the beaker a few times, pour, wash again and pour. Do you remember? So that is the part on dissolved solid and it's washing. And it must be into a 250 cm cube standard flask. Okay? After you transfer already, the volume is still quite little, so what do? Correct. Add in more water. You cannot just say add in more. You cannot just add in more. You need to correct. Fill to the line, meaning fill to the mark. Okay. Make up to the mark with distilled water. After you make up to the mark with distilled water, what's the last thing?
Shake man.
Correct. Shake to give a homogeneous solution. Okay? Homogeneous solution, and you can label it Fa2. You can label it Fa2 so as to allow you to next step, right? Yeah, easier to refer back to it. So everybody take note, this is prepare standard solution, only just 5 steps. Can? So moving on, right? Another scenario. If you want to analyze some tablets, what would you do to the tablets first?
Throw the floor.
Crush, correct. Crush the tablets first.
See whether got the apples there.
Huh?
Tablet, I got iPad.
Okay. Grind the tablets, Grind the tablets. So if you want to analyze one tablet, you grind everything and then place everything straight away dissolve. Straight away go to step 2. Straight away dissolve. But if you want to analyze half a tablet, you still need to go on to step 1 and say how much you want to measure out. Is it okay? Can I move on? Yes. Okay, next part. Yeah. Huh? Go up. This one I will upload to the LMS. But of course the main thing over here is really understand what is happening. Okay, next part, I need you to take note of this part. Label again, split it up into titration procedure. Titration procedure will start from the pipetting. Okay, so over here you have your 250 cm cube flask. 250 cm cube flask. If you have a 250 cm cube flask, how many titration can you do? 10, right? Correct. Because each time you pipette out 25, you can do 10, many titration. So over here, usually what is in the conical volumetric flask, you can pipette out. So pipette 25 cm cube into a 250 cm cube volumetric flask. Sorry, conical flask. And in this case, always remember, this part, if you are talking about redox titration, you always need to acidify. Correct. Equal volume of dilute sulfuric acid, and you know that the concentration is 1 mole per dm cube. Everybody take note. This one is to really ensure an acidic medium. Is it okay? After pipetting, okay? Because this part, right, is just a volume for me to ensure that it's in excess. If I want to use 50 cm cube, can, but it's just like I know that 1 mole per dm cube is quite concentrated. I add the same volume, which means 25 is already in excess, so it's okay. No. Because every time you pipette out 25, so you just need to add another 25 cm cube of sulfuric acid. It's okay already. Just equal volume, just to ensure that it's in excess. If you want to use 30 cm cube, 50 cm cube can, but 50 I think is too much. Later you swirl the conical flask, right? Every solution will just fall out of the place. Okay? Huh? Yes. Okay, class, this next part, right, take note. You have C2O4 2 minus and KMnO4. You have KMnO4. The ions are oppositely charged. If the ions are oppositely charged, you will repel, right? You will repel.
Oppositely charged.
Opposite. They are the same charge. Yeah, same. So they will repel. If they repel, the reaction will be slow. So that means you need to heat up the solution. Heat the solution on a hot plate to about 70. Okay, on a hot plate to about 70. And then after that, please take note, after you pipette already, you must prepare the burette, right? So always remember, you transfer the other solution into a burette and then titrate the warm Fa2 against Fa1. And this part, take note, stop titration when the solution turns from yellow to orange. Okay, turns from, run the warm Fa2 into? Why run? Because the correct term is titrate. Okay, so everybody, I want you to take note of the color change. Initially, right, in your conical flask, what is present is your C2O4 2 minus. The color is colorless. When you actually add in your dark red FeO4 2 minus, okay, FeO4 2 minus is dark red. The FeO4 2 minus will become Fe3 plus. Fe3 plus is what color? Pale yellow. This part take note. Fe3 plus is pale yellow. It is Fe3 that is plus. Okay. So take note. Fe3 plus is pale yellow. So that means as you react, right, you will find that the solution slowly becomes yellow color. Okay. And then you know that on top is actually red color. At end point, you add one more drop of red. It's red plus yellow, you'll get orange. Yeah, so that's why the color change over here is to orange color. Okay, from yellow to orange. Everybody okay? And then finally, you stop titration, repeat titration until you achieve consistent results. Okay, class, I may have marked your paper wrongly. You check that the answer is actually yellow to orange and it is Fa2 and Fa1. Take note, if I mark wrongly, you just cancel. Everybody clear of the thinking process? Can? So for titration, we also only have 5 steps. Titration mainly starts from pipetting. Pipette already, then you prepare burette, titrate, take note of the color change, and then repeat titration. 5 steps. 5 steps each. Is it okay? Can I move on? Why are you all copying? I mean, it's only some blanks, is it? Yeah, I said I marked wrongly, so you just correct it on your own. Okay, class, for part E, do you need me to go through? Part E. Huh? Okay, please pay attention. Part E. In the student's titration, okay, she found that X cm cube of Fa1 reacted exactly with Y cm cube of concentration M. Take note, your Fa2 is actually your C2O4. Your Fa1 is your FeO4 2 minus. Okay? If you have your concentration and volume, you can find moles, right? Concentration times volume. You will get M times Y over 1000. Y over 1000 because you are changing to, yes, correct, to dm cube. Over here, check your mole ratio. C2O4 is to FeO4 2 minus is actually 3 is to 2. So your number of moles of Fa1 is simply just times 2 over 3, okay? This is by proportion. Okay, by proportion. So concentration is very simple, right? Concentration is just mole over volume. So you take the number of moles, divide by the volume needed is X. x cm cube, cm cube to dm cube divide by 1000. Okay, you should be able to get 2my over 3x. Okay, this question, you notice that the question says outline. Outline how you will use the result. You don't need to say things like, firstly, find number of moles. Next step, find concentration. Don't need. You just need to write as per normal how you would do a calculation. Is it okay? For the next question is simply just safety precautions, right? Okay, safety precautions, you all just quickly jot down. Can I move on from here already? Can, right? Okay. Safety precautions, very simple. You just see what you are using. Okay, if you are using sulfuric acid, usually we just say it's corrosive. Okay, corrosive means wear safety goggles and gloves. And the compound that you use, they are toxic. Again, wear safety goggles and gloves. Another part is you may have prolonged heating. Prolonged heating will cause the solution to bubble over, and you can cause scalding. So again, you can just wear safety goggles and gloves. So you notice every precaution is the same. Just wear goggles and gloves, but your reasoning is different. Maybe one is corrosive, one is toxic. Or you have prolonged boiling, you need it to spill over. Yeah, just one. Out of these three, just one. Question 2, right? Remember, just now we were talking about redox titration. Now we want to move back to acid-base titration. So this one is our acid-base titration. Can everybody? So over here, we have sodium carbonate. We are supposed to titrate with standard hydrochloric acid, okay, in order to determine the value of X. So based on this part, right, take note, your Fa1 is 3.6 gram of solid hydrated sodium carbonate. Fa2 is dilute hydrochloric acid and other laboratory chemicals and apparatus. So based on this part, right, balance equation, I think everybody knows, so I'll move on. This part, I know some of you have some answers already, but when you write volumetric analysis, please be systematic. We start off with the prepare standard solution. Okay, remember for color, class, in this case we are titrating Na2CO3 with HCl. Okay, this one, yes, that means you split out into prepare standard solution and the actual titration procedure. So this part, can you please take down? You have the sodium carbonate and you have the HCl. You actually have a choice. Which one do you want to place inside the conical flask? So in this case, you just need to check the color change. Color change is usually lighter to darker color. Okay? This one must be lighter to darker. Okay, the color change should be lighter to darker. So before we even start, let's check. This one is a weak base. This one is a strong acid. So strong acid, weak base titration, pH equivalence point, correct, less than 7. Indicator must be correct, methyl orange. So if you take a look at this range, not here, sorry, methyl orange. Okay, methyl orange, right? In acidic medium, what is the color? Red. In alkaline medium, what is the color? Yellow. In between endpoint, orange, correct. So over here, what color change do you want? Do you want red to orange or yellow to orange? Yellow to orange. Always from lighter to darker. Easier to see the color change. So we use yellow to orange. Class, so if you want yellow to orange, right? What must you put inside the conical flask? What will give you a yellow color? Na2CO3, right? Is a base. So alkaline give you yellow. So over here you must put Na2CO3 to get a yellow color first. Is it okay? Can? So this part, take note. You have the 3.6 gram. So again, you need to weigh 3.6. Weigh 3.6 using what? Using a mass balance. Weigh 3.6 gram into a 100 cm3 beaker. Okay? 3.6 into a 100 cm3 beaker. Okay, can? Yeah. After you weigh it into a beaker already, what do? Dissolve in what? Can you dissolve in dilute H2SO4? This titration is acid-base titration. Can you anyhow just add H2SO4? No. So what do you dissolve it in? Correct. Distilled water. You cannot add any acid. This is acid-base titration. Is it okay? So we can only dissolve it in distilled water. Take note, So there is one difference between redox and acid-base titration. When we dissolve the solid, for acid-base we must definitely use distilled water. For redox, right, use the dilute sulfuric acid. Is it okay?
Yes.
Yeah. So based on this, we know distilled water. After distilled water, what? Transfer the dissolved solid and the washing into the 250 cm3 standard flask, not distilled flask. Yeah. Then you must remember properly. Okay, it's called standard flask or volumetric flask. Everybody okay? After you transfer already, what do? Top up to the mark with distilled water. Okay? And then finally, shake well to give a homogeneous solution. Over here, right, you can label Fa3. Okay? You can label Fa3 because the question already got Fa1 and 2. Just label Fa3 to distinguish it from the others. Okay, so again, just 5 simple steps for preparing standard solution. Okay, just 5 simple steps for preparing standard solution. Can everybody? After you prepare standard solution, what is the next major step? It will be the titration already. So can I move on to the titration? Yes. So after that, you can speed up your working into titration procedure. Okay, so for titration procedure, take note, over here you have the Na2CO3, pipette out 25 cm3 into 250 cm3 conical flask. Take note, 25 cm3 into 250 cm3 conical flask. Okay, class, before you continue, right, what do you need to do to the conical flask?
Wash.
No. This is an acid-base titration. What do you need to add in? The 3 drops. Indicator. Okay, can? So you quickly identify if the question is an acid-base titration. Remember, you need an indicator. So that means next step, add indicator. If you add indicator, what color will you get? It is base inside. You should get what color? Yellow. Correct? Because it's a bitter orange in base. So take note, you should get yellow color. You get yellow color. After that, what do? Transfer what into a burette? Transfer what into a burette? The Na2CO3 is inside the conical flask. What is your other reagent? Correct. HCl inside a burette and titrate with Fa3. Then last step is titrate, stop titration when the solution turns from what to what? Orange, correct. Okay, titrate from yellow to orange. Correct, remember just now we go through the color change of the indicator. Initially it's yellow, finally it's orange. Last step, Diana, what's the last step? Repeat until? Correct. Okay, good. So again, just 5 simple steps for titration procedure. Okay? Yellow to orange.
We do have to put an outline and
Huh? Class, everybody go and find out phenolphthalein, what is the color change? Huh? Colorless to permanent pale pink. Colorless in what medium? Correct. Can I move on from here? Can I? So I'll move on. Can I move on? Yes, right. This one is the same as the previous one, right? Just 5 same steps. Okay, so I move on, okay? Yeah. You can go back and check also. So this part, titration, she found that 25 cm cube of Fa1. Fa1 is our HCl. It reacted with 24 cm cube of Fa2, 0.1 mole per dm cube. Outline how you will use her results to determine value. This one, I will just give you the, can you please check? Concentration times volume, you can find mole. That is for HCl. Then after that, for Na2CO3, you know that that was in 25 cm cube. But you know the mole ratio is 2:1, so you need to divide by 2. But again, you know that originally you took out from the 250 cm cube volumetric flask. So originally it was in 250 cm cube. So now you want to find the moles, right? You need to times 10. Agree? Times 10. And you can find the MR. Because you have the mass. The mass is 3.6. MR is equals to mass over moles. So you take 3.6 divided by the moles, you get the MR. And in order to find the X, you just take this minus away the Na2CO3. And you divide by 18 to get X. 18 here refers to the H2O. Okay, you can take a picture, then I'll move on already. Okay, can I move on?
How to take without you?
You just did it, it's very bad. Okay, next we move on. Okay, last one already, the procedure, right? They say that instead of titration, they can do heating, thermal decomposition. Take note, this is thermal decomposition. Okay, for thermal decomposition, right, it is supposed to drive off the water of crystallization. So you actually weigh a crucible and record the mass. So at between 2.5 and 2.7, record the new mass. They say heat gently and then allow it to cool, and then weigh the crucible and its contents, record in the table. However, this method is very, very not accurate, less accurate than the titration. Okay, titration is usually taken to be a very accurate way of determining all these X and whatever. Okay, so over here, okay, they say that they calculated a value X that is less than the true value. If your value of X is smaller, that means your water loss is greater or smaller. Because X is dot H2O. If your X is smaller, lower than actual, that means your water that is being lost is more or less. Huh? Should be lesser, right? Okay, your X is smaller than the true value, that means your amount of water loss is definitely less. So based on this suggest an error, what will cause the water loss to be less than usual? That means your heating must be correct, insufficient, or what happens? Either your mass loss is too low because didn't heat enough, or you heated enough but after that it take back, correct, reabsorb. Very good. Okay, it reabsorb. So based on this, right, they say suggest a modification. Modification for insufficient heating. Remember the process for thermal decomposition? We always repeat the heat-cool way process. Remember? Repeat the heat-cool way process until you have a constant mass of residue obtained. Residue means simply whatever is left inside the crucible. Okay, Ken? Take note of your residue. You are talking about constant mass of the residue. And of course, this is to ensure that the water of crystallization is completely driven off, and this will ensure that the mass loss will not be too low, and hence value of X will be nearer to the true value. Everybody okay? So if the insufficient, what else can you do to the solid? If the solid is in big lumps, that's why water cannot escape, right? What will you do? Yes, correct. Maria mentioned obtain a larger surface area by doing what? Pounding, right? Grind the solid first. Okay, grind the solid to obtain a larger surface area. Okay, if you want to copy, right, the last two parts is actually the same, so don't need to copy 2 times. Is it okay? Can I move on? Everybody? Can, right? Okay, next one, if you don't want it to reabsorb moisture, what can you do? You can put what inside? The one that you find in your shoe. The not mothball. It's the not that. Not boiling tube, the silica. Silica gel, correct. Your silica gel is your drying agent. Okay? Okay, either you cool it in a apparatus with some drying agent, okay, or you can cool the solid by putting on a lid. So you put on the lid, right, it cannot absorb the moisture from the surrounding. Is it okay? Can? Okay, class, FA4 I haven't finished going through, so what I want, should I do a video and then y'all go and check?
Okay.
Can I do a video? I do a video, so y'all go and check it on your own. Is it okay? Can. Before y'all go off, right? Please take this down. For those of you who haven't finished the revision package, right? Because for the revision package, if you haven't finished all the questions, not to worry. I just selected a few questions that is more relevant to our mid course, right? You go and try it out. And also please try the MCQ package. Y'all know what is the revision package or not? Yes. Yes, right? Okay. And 2010 and 2011, the solutions are okay. A-class, the solutions, right, I will upload onto LMS. And for the FA4, everybody for FA4, right, when I upload to LMS, where will it be found? It will just be in our usual, Playlab, correct, okay? Similarly, for today's tutorial, right, I will just put the video there. Anything you miss, you're just going to take. Can? Yeah. So, Can. So everybody, just want to say all the best to everybody. And next year, I hope that all of you will progress together in class. Okay? Everybody work hard for your different subjects and hope that everybody will be promoted together as a class. Is it okay? Thank you, Okay, so that will be the end of the tutorial. Everybody good luck. Yeah, if you still need to have any consultation, right, you can fill the slots. Okay, otherwise, you can go first. Thank you, everybody.